Okay. Hello, everyone. Today, we're very happy to have Dr. Uh, Hyung-Mi Cho to give us the last talk in the year of 2022. Hyung-Mi is currently working at the Department of Ocean Sciences in Inha University. She got her bachelor degree in oceanography in 2009 from Seoul National University. And she got her PhD in chemical oceanography in 2017, also from Seoul National University. After that, she worked with Gubon Kim for another 3 years as postdoc researcher. In 2020, she got her current position as an assistant professor at the Department of Ocean Sciences in Inha University. Her research interest including investigating the fluxes of SGD and SGD-derived nutrients in coastal waters, also in global oceans. Nutrient behaviors in subterranean estuaries, cross-shelf transport of nutrients in the northwest Pacific Ocean, and analysis of radionuclides in various environmental materials, such as rainwater, seawater, marine organisms, etc. Today, the title of her talk is Submarine Groundwater Discharge from a Volcanic Island, Jeju, Korea. Okay, Hyung-Mi, time is yours.
Okay, thank you for arranging this presentation and introduction about me. Thank you for Buchao. And hello, everyone. Good morning and good afternoon and good evening, everyone. It's 10 p.m. in Korea. And thank you to everyone who came to hear my presentation. And these photos are beautiful scenes of Jeju Island and this stone, 돌하르방 in Korean. It's a stone statue handed down from Jeju Island, a symbol of Jeju Island. And this translated to stone grandfather in Jeju language. Okay, actually, as the title suggested, I try to review only the research results related to groundwater in Jeju Island. But given this opportunity to have a presentation, I'd like to introduce the overall research field first, although Chao had already introduced. And this is a simple schematic of my research. And this could be categorized by spatial scale into 3 groups. And topic 1 includes the SGD flux and associated nutrient fluxes and their impacts on coastal environments. And regionally, this study was mainly conducted in Jeju Island, and research was also conducted on a global scale. And topic 2 is about cross-shelf fluxes of nutrients and dissolved organic matter. And the study was conducted mainly on the continental shelf of the East China Sea, located in the Northwest Pacific Ocean. And the topic 3 is about vertical flux of nutrient and export production of organic carbon in the ocean. And this study was conducted in the East Japan Sea, and a paper was recently published. And among these topics, today, of course, I'd like to show the results of on topic 1 on a global and a regional scale. So both figures show the coverage of SGD study sites and SGD fluxes globally, as outlined in these figures. SGD study, the research has been mainly conducted in the European Union and North America and East Asia. And the increasing trend for the research publication with keyword submarine groundwater discharge in recent 20 years. In addition, the spatial scale of the estimation based on geochemical tracers can vary from meters to global scale and overcome the covering more than 30 sites in the past 40 years. Even when I first started studying SGD, it was at a time when its importance on a regional scale was rapidly emerging, but no estimates are available for the SGD flux and SGD contribution to nutrient cycles in the global ocean. So while the global estimates are were available on nutrient inputs via river discharge and atmospheric deposition on the global ocean, but there were no estimates for the SGD flux on a global scale at the time. So as you know all too well, it is difficult to, due to heterogeneity of groundwater seepage over spaces and times, and groundwater flow is unseen. So in a SGD studies, this radium-228 or 22643, the radium isotopes have been used successfully for tracing SGD in basin scale. In the Mediterranean Sea, SGD flux was equal or larger by a factor of 16 than the river discharge. And in the Atlantic Ocean, SGD flux rivals river discharge. And these are very representative SGD SGD findings at the ocean basin scale. A simple way to use the information provided this iStop is to make an observation-based inventory of the ocean radium-228. At steady state, the supply of radium must balance the loss from disintegration, and this direct approach suffered from strong potential biases when the data are sparse, and because the total amount of radium in the ocean is then roughly estimated using regional averages of observations or linear interpolations. So it is suitable only in regions with dense sampling like this, such as Atlantic Basin. So it was very difficult to apply this method on a global scale due to the limitation of data almost only to the surface in the Pacific Ocean. So it was impossible to obtain the upper ocean inventory of radium as calculated in the Atlantic Ocean study. So to solve this issue, I decided to apply radium inverse model by recasting Dr. Eun-Young Kwon. Actually, I'm not very good at modeling. I'm not a modeler. I'm a person who has always been an observation. So this inverse modeling techniques represent an alternative and powerful approach to estimate the fluxes, providing that ocean circulation is known with sufficient accuracy. So using this model, we found that SGD flux is 3 to 4 times the river fluxes. It's very huge amount, but converting the radium flux to flux of SGD introduces further uncertainty with respect to constraining the tracer and member values in groundwater. So the next objectives of my study were to examine the characteristics of radium in coastal groundwater. So the total groundwater samples include both the saline and the fresh groundwater. So the effective of groundwater salinity on radium and member values can bias magnitude of SGD. So for a simple comparison, the radium data were sorted into 4 different salinity ranges. As a result, the concentrations of radium isotopes are higher in higher salinity ranges with much lower activities in fresh groundwater, the salinity under 10. It seems to be due to higher ionic strengths in higher salinity water. So this first order approximation shows that radium and member values are greatly dependent on groundwater salinity. So as you can see, all the compiled data show that radium concentrations are quite constant at salinity values over 10. And in order to offer a conservative value and avoid the overestimation of SGD flux, observations from fresh groundwater, the salinity value under 10, were excluded from the data set in my study. And as you can see in this table, the groundwater radium to 28 and members are similar for this higher salinity ranges, which are 2 times higher than the value using the total data, including fresh groundwater samples. So re-estimated SGD fluxes using data with salinity 10 are 2 times lower than the value using total data set. And based on many seepage experiments conducted throughout the world, I thought it is reasonable to use the data for salinity over 10 and recalculated SGD fluxes into the Atlantic Ocean and global ocean in this study are approximately 2 times lower than values from the previous studies. So the re-evaluated global flux of SGD is 1 to 2 times the 2 times the river fluxes in the ocean. And after revealing that groundwater discharge is as important as river runoff, I wondered how much nutrients would be supplied into the ocean through SGD. So in order to estimate global SGD-driven nutrient fluxes, I collected the data for dissolved inorganic nutrient concentrations with radium-228 in coastal groundwater. And these are data collection sites for nutrients and radium in global coastal groundwater. And I used the flux of radium through SGD into the global ocean, which is obtained by Kwon et al. By using the radium inverse model. So as a result, SGD-driven nutrient fluxes to the global ocean are shown in these bar graphs. This baby pink color bars represent SGD-driven nutrient fluxes using total data, and the dark pink color bars means the fluxes of SGD, fluxes of nutrients by SGD using the data for salinity over 10. And blue bars represent the river discharge, the nutrient flux from river discharge. So the fluxes of DIN, DIP, and DSI estimated using data for salinity over 10 are 30%, 80%, and 20% of those estimated using total data set respectively, which are comparable to riverine fluxes to the global ocean. So in conclusion, groundwater and member values are primarily dependent on groundwater salinity, and based on this calculations, the results suggest that previous estimation of SGD flux to global ocean could be overestimated approximately twofold, and therefore more extensive studies are necessary to accurately determine the groundwater and member values, because the SGD-driven fluxes of chemical constituents into the ocean have great impact on coastal biogeochemistry. So since then, values for nutrient fluxes to groundwater have been updated by other many researchers. So in next step, now I will show you regional scale studies. So as you know, SGD is an important pathway of nutrients and also other chemical constituents in coastal ocean. So this SGD is particularly important in land islands where no large river discharge and precipitation is large and rocks are highly permeable. So furthermore, nutrient fluxes through SGD are very important in coastal waters of islands, especially standing in oligotrophic oceans. There are many local studies on ecological importance of SGD in coastal waters of islands. So do you know where Jeju Island is located on this world map? On this global map, it's so small you can't even see it. And here is Korea, and this little tiny dot is the Jeju Island. But many people will be surprised how important and diverse the role of SGD plays is on this tiny island. Jeju Island is South Korea's largest island, covering an area of 1,833 square kilometer, which is approximately 2% of the total area of the country. And it is also the most populous island in South Korea. This island lies in Korea Strait here, south of the Korean Peninsula and south is Jeolla province. And now I'm at Inha University in Incheon, next to Seoul. Here, it's near Incheon Airport. So when I studied in Seoul, and now it takes an hour by plane to this Jeju Island. And it has an oval shape of 73 kilometer east to west and 31 kilometer north south with a gentle slope around Mount Halla in the center. And the length of the main road is 181 kilometer and the coastline is approximately 420 kilometer. And this the length of the coast of Jeju Island is 3.5% of the total coast of Korea. And this island was formed by the eruption of an underwater volcano approximately 2 million years ago. And the volcanic island consists chiefly of basalt and lava. So this island has a humid subtropical climate and a temperate climate, which is moderate even in winter. The temperature rarely falls below 0 degrees Celsius. And Jeju is a very popular holiday destination, and a sizable portion of the economy relies on tourism and related economic activity. So it is sometimes called South Korea's Hawaii. And due to this extensive tourism, the pollution of beaches has become a serious problem also. And the picture below, they were taken when I visited Jeju Island with my husband in the May of last year. I was about 20 weeks pregnant at that time. And my husband, he studied trace metals in seawater. And anyway, there are common scenes that can be seen in Jeju Island. So I want to show you this beautiful scene in Jeju. So volcanic island Jeju is located approximately 100 kilometers of the southern coast of Korean Peninsula. And the 90%, more than 90% of this island is composed of porous basalt, and the half of around 50% of the total precipitation contributes to groundwater recharge, and there is large difference in geological structures and the occurrence of groundwater between western and eastern part of Jeju. On the western part, under the thick basaltic layer, the low permeability Sekipo formation is continuously distributed. So the majority of the inland groundwater in this western part uh, occurs occurs above low permeability rocks without contact with seawater. So there are numerous springs and wells on the western part of the island. So fresh groundwater as dominant system, while unconsolidated fine sand layer underlies the basaltic rocks in the eastern part. So in the eastern part, the subsurface water below a few meters is almost completely composed of recirculating seawater. So it has very different types of groundwater between the western and eastern parts. So groundwater is the major source of water used in Jeju Island. And due to highly permeable surface conditions, the island does not have any perennial streams or rivers, no large rivers. So accurate estimation of ground recharge and understanding groundwater system are critical to make a reliable water budget in this island. So as I mentioned before, almost half of the precipitation infiltrates into subsurface layers, and the groundwater recharge may be balanced by rapid discharge to the ocean and withdrawals for public water supply. And based on many observations and estimations, now we know that submarine discharge of groundwater appears to have a large effect on the budget of fresh water, nutrients, and chemical species in coastal ocean of Jeju Island. And the submarine fresh groundwater flux during the study period calculated from a freshwater budget of the water column was 4.5 multiplied by 10 to the 6 cubic meter per year, which is close to the long-term average based on inland water balance. However, the saline submarine brackish groundwater discharge accounts for 10 times more. And also the coastal seawater near Jeju Island, the characteristics of currents around Jeju Island, it's Tsushima current, which has high salinity and low nitrate concentrations because it originated from oligotrophic Prasho current. And this current often diluted by Changjiang River diluted water in late summer and the fall. So the CDW has relatively high MP ratios, which exceed 100. Okay. So Jeju coastline is 0.08% of the global coastline. In order to determine the importance of SGD-driven DIN over the entire island, the average of coastal groundwater DIN concentrations measured in this island was multiplied by Jeju's total SGD. So seepage measurement from one station showed relatively little seasonal variations. So this estimation appears to be reasonable for representing this island. So this DIN flux is larger than obtained through some large rivers such as Delaware and the Fraser. although it is approximately an order magnitude lower than the world's major rivers, such as Amazon, Changjiang, and the Mississippi rivers. And the DON, the yellow bar, DON flux from the entire Jeju is comparable to some of the world's largest rivers here, such as Delaware or Fraser River, in a semi-enclosed bay. Here, Hassan, this case study shows that the DON removal by biological utilization was ineffective, while DIN removal was very effective. The 90% of SGD driven dissolved inorganic nitrogen effectively removed in an inner bay system. So therefore, the SGD driven DON in Jeju Island seems to be an important nutrient source in offshore waters, while SGD driven DIN is readily utilized by phytoplankton in nearshore waters. And the concentrations of trace elements in groundwater and seawater were measured in the coastal embayments of Jeju Island. Overall, the concentrations of most the trace elements in groundwater were 3 to 74 higher than those in the seawater in Jeju Island. So simple budget calculations shows that large fluxes of SGD-driven nutrient, the trace elements were responsible for the unusual enhanced concentrations of trace elements, particularly for iron in the seawater. So this iron flux through SGD from Jeju is 0.2 to 0.7% of the global riverine flux. Since I don't study trace elements well, so I'll briefly mention about the results and move on. In conclusion, in Jeju Island, SGD is an important source of not only nutrients, but also the trace metals and rare earth elements also. So, okay, from now on, I will show the results of research by reason in the form of a review. The first study site is Hwasun Bay here, which is located in the southwestern part of the island. And the area of this bay is 1.4 square kilometer, and the average depth is 8 meter. And there is no continuous stream flow or river discharge into the bay. There are abundant meteoric groundwater springs, and we can observe very high seepage rate, and fresh groundwater is the 25% of the total SGD. So we can collect coastal groundwater samples and seeping groundwater samples and seawater samples like this. And can you recognize the people in this photo? This is Billy Moore and Tom Church. That was in 2013, so almost 10 years have passed now. So they had come to Jeju Island to attend the SGD symposium hosted by our research team, Kim. At that time, I was a graduate student, and the place they are looking at is Hwasun Bay here. And I just wanted to show them the SGD site that I was investigating, I was studying. So these are the observed data from Kim et al. In Hwasun Bay. In the course of mixing between offshore water and coastal groundwater, the removal of DIN was significant inside the bays, whereas there was an addition of DIP in the space system, and DSI shows relatively conservative behaviors. So you can see the large discrepancy between DIN and DIP due to large differences in MP ratios between groundwater samples and the inner bay samples and outer bay samples. This means that the ion introduced into the bay could be removed very effectively in the low MP ratio and in the nitrogen depleted coastal waters of Jeju. However, it appears that DIP flux due to the diffusion from the bottom sediments was larger than the amount of DIP removed by biological uptake. So in order to calculate the net removal of DIN inside the base, we constructed a DIN mass balance model, which can be expressed as follows here. So where F, this term as DIN flux by diffused from bottom sediment, and this term is the groundwater DIN concentration, and this is the DIN concentration in the bay water. So F removal is DIN removal by biological production, assuming that the other removal factors are negligible. So based on this mass balance model, about 90% of SGD-driven DIN was consumed inside the bay. And if we assume that this removed DIN was fully utilized by primary production using Redfield ratios, which potentially supports about 1,000 milligram carbon per square meter per day of new primary production. And observation in this area continued after that. 2 more sampling campaigns were conducted in October and May. In fresh groundwater, the mean concentration of DIN and DIP were quite constant over the 3 periods, and the temporal variations of nutrient concentration in groundwater were insignificant relative to spatial variations. So the concentrations of nutrients in coastal seawater decreased as salinity increased during all sampling periods. So the large anomalies of salinity in the bay seawater were observed in the May sampling campaign. So considering that there is no surface runoff, so the salinity anomalies reflect the influx of fresh groundwater into the bay. So this fresh SGD flux can be calculated based on salinity anomalies in the inner bay seawater relative to the outer bay seawater, together with the water residence times of the bay. So the so the contribution of fresh groundwater inputs to Possum Bay seawater was estimated by multiplying submarine fresh groundwater derived nutrient fluxes by water residence time. And remember concentrations of fresh groundwater. So the nutrient contributions to the bay seawater from fresh groundwater to the background concentration of outer bay seawater was simply compared right here. So the contribution of outer bay seawater to nutrient inventories of this Possum Bay was estimated by the multiplying mean concentrations of nutrients in outer bay seawater by the volume of the seawater. As a result, in August here, on the basis of this estimation, approximately 40% of the ion inventory of the inner bay was found to be from fresh groundwater, the light blue, the sky blue color, whereas the contribution of outer bay seawater to the DIP inventory of the inner bay seawater was 99%, and dissolved silicate input via fresh groundwater contributed approximately 20% of the DSI inventory of the bay in August. And this results show that inputs of DIN from SGD contributed significantly to biological production in this bay. And in October, the submarine fresh groundwater fluxes were lowest among the three sampling periods. During this period, DIP inputs through as the submarine fresh groundwater contributed to about 100% of the DIP inventory of the bay, but in May, approximately 60% and 25% of DIN, DIP, DSI inventories in the inner bay system were respectively attributed to SF, the submarine fresh groundwater discharge. So in Hudson Bay, the concentrations of nutrients in coastal groundwater samples were similar for the different seasons, but the potential of SGD-derived nutrients on biological production was very different from for the three sampling periods. So further extensive studies are necessary for understanding this large seasonal and spatial variations of groundwater-derived nutrients input to this coastal bay system and their different roles in coastal production. And this is the results of a more recent study conducted in Hudson Bay. It is investigated monthly environmental factors where the SGD is major source of terrestrial substances as reported in previous studies. The sampling campaigns were conducted monthly during 2019, and the scatter plots between dissolved silicate and salinity in each sampling campaigns. And the dotted line indicates the regression line. And the to estimate seepage rate of FSGD, the fresh groundwater, fresh SGD in Hudson Bay, the silicate mass balance model was applied. And in Hudson Bay, silicate concentration in fresh groundwater was 10 or 10 to 100 times higher than that in seawater. And they show significant negative correlation with salinity for fresh groundwater, saline groundwater, and bay seawater, and the open ocean seawater, suggesting the fresh groundwater-derived DSI is conservative and additional sources are negligible. So we can use this silicate as a tracer to estimate the submarine ground discharge flux in this bay system. And during January to July and November to December, the seepage rate of FSGD remained relatively low, constant at 3 plus minus 1 centimeter per day, and high seepage rates were observed from August to October, along with a relatively high precipitation rate. Typically, the East Asian monsoon lasts from July to August in Korean Peninsula. And in September 2019, the sampling period, precipitation of 500 millimeter was recorded in Jeju Island, which was significantly higher than the average values of monthly precipitation, around 100 to 200 millimeter, perhaps owing to frequent typhoon events in this season, the typhoons Ling, Tafa, or Maitak, such as these typhoon events affect the large precipitation and large the seepage rate. So on both sampling campaigns in September 10 and 24, heavy precipitation was recorded after Typhoon Ling, and relatively high seepage rates were observed. And therefore, the transport of groundwater via SGD in Hudson Bay was significantly increased by heavy precipitation from the East Asian monsoon and the typhoons. And SGD-driven DIN flux in Hudson Bay almost doubled not this data, doubled in 10 years. And in a previous study, the DIM flux via SGD in 2010 was reported to be approximately 3 multiplied by 10 to the 5 mole per day, which is approximately half the value determined in this study. The seepage rate of SGD in the same study was twice the value obtained in this study. This figure shows the annual variation in DI and groundwater samples around the Hasan region, in the distribution of nitrate concentrations in groundwater in Jeju Island. Despite the large uncertainties in the estimate, the result is supported by that the nitrogen contamination in coastal groundwater is increasing, and the nitrogen contamination may be caused by excessive use of liquefied and chemical fertilizers in many farms, the tangerines and vegetable farms. So, especially the ice-top ratio indicate that the anthropogenic fertilizer is the major source of nitrogen contaminants. And the very high DIN flux during spring season, even for low spigulate, the black straight lines, even for low spigulate, the very high DIN flux was observed in this spring season. It can be attributed to the nutrient contaminations in coastal groundwater. Here in spring season, very high DIN concentrations were observed. So perhaps it is because of the excessive use of fertilizer input from the ground, the agriculture activity. And the large variations of the SGD-driven nutrient fluxes seems to be derived from precipitation and anthropogenic activities near the study region. And this study suggests that a long-term investigation is required to estimate the representative values of seepage rate of SGD and the flux of terrestrial substances to cover various environmental and anthropogenic factors during different seasons. And during this study shows the another result, the SGD and pH in coastal water. So during the past few decades, excessive input of nutrients and organic matter, in addition to global ocean acidification, has resulted in significant changes in the water pH of coastal ocean. So this study shows the effect of SGD on pH variations in the coastal waters of the Hudson Bay. So seawater samples were taken from 11 stations, and the 8 stations were selected as potential points affected by SGD within Hudson Bay, the stations 1 to 8, and 3 stations were selected as offshore seawater and members, and also groundwater samples were taken. And we can show this low salinity plume zone, and also the same region, the pH was higher than that in other areas. In contrast, the concentrations of DIC were lower than those in the other areas and consistent with low groundwater and members. So for the entire bay, both the pH and the DIC concentrations show significant linear correlations with salinity. And because the salinity in this bay mainly dependent on SGD, these relationships suggest that SGD dominantly affects the pH and DIC of the seawater. And these are my colleagues. They said the simple mixing between groundwater and seawater cannot explain this positive pH anomalies. So this such large pH increases must also result from other processes like photosynthesis and dissolution of CaCO3, and the negative DIC anomalies discount a contribution of CaCO3 dissolution. So they examined the effect of photosynthesis produced by the DIN input from SGD. So a simple two-end member, the submarine groundwater and offshore seawater mixing model show that this pH increase was caused by enhanced biological production, which resulted from the SGD-derived nutrients input. So just dilution by groundwater accounts for up to 10% of the positive pH anomalies. So the remaining pH change is found to be caused by enhanced biological production fueled by SGD-driven nutrients. So this effect of SGD on coastal pH is clearly observed in this simple SGD dominant system. So they suggested that SGD may have a significant influence on coastal biogeochemical changes, such as acidification and eutrophication, since a number of local and regional studies show that SGD-driven nutrient fluxes are comparable or higher than riverine fluxes. And we can move on the north part. So this in this Jocheon Harbor, these kind of green tides have resulted in many problems, stink, smells, and deposited of drift green macroalgae on shorelines. So the occurrence of these green tides in the eastern coast of Jeju has been speculated to be due to marine environmental changes together with geological factors. So this kind of green tides occurs in Jocheon Harbor, which is very small bay located in the northeastern part of Jeju Island. And there are over the 6 groundwater springs in Jocheon, and water samples collected from Jocheon Harbor and adjacent groundwater wells in July 2015, August 2015, and February and March 2016. So seawater samples from the surface and bottom layers were collected using electric submersible pump on shipboard, and fresh groundwater samples were collected from groundwater wells, and saline groundwater samples were collected from seepage chambers by scuba divers. So we used modified lead-type manual seepage meter to collect spin groundwater. And this collected bag was attached to nipple ball valves at the top of the chamber and measured the groundwater samples in the bag were measured for salinity, radon to 22, and nutrients. So since submarine fresh groundwater is the major source in this harbor, we can determine the magnitude of SFGD using a radon tracer. And based on this radon to 22 mass balance model, as the submarine fresh groundwater flux is estimated to be approximately 7.6 to multiplied by 10 to the 4 cubic meter per day, and these results were almost similar to those measured by the speech meter. And based on the simple mass balance model, on this budget calculation, the flux of DIN through submarine fresh groundwater discharge contributes approximately 80% of the total flux, and the DIN flux through the submarine fresh groundwater enhanced approximately tenfold of the ion level in this harbor seawater. And in order to evaluate the effect of submarine fresh groundwater on the growth of green macroalgae, in situ mascosm experiments were conducted. So the thallium uva species for mesocosm experiments were collected from Jocheon Harbor and rinsed gently using 0.22 micrometer filtered seawater to remove small grazers. And in order to the sample disk of ova, the adult thalli were cut using pork bore and allowed to recover from respiration and wound for a day. And mascosm experiments were conducted during 5 days between April 26 to 30 in Jocheon Harbor. And the culture was carried out at 27-liter chamber covered with polyethylene film. And for the experiments, 1 control seawater and 5 different mixtures of open ocean seawater and fresh groundwater were prepared. And the mixing proportions of fresh groundwater to the open seawater were 1% to 50%. And all experiments were incubated under natural temperature and irradiance conditions. And as a result, and the growth rate of ova was calculated using this equation, and where T is the incubation times in days, and A0 is the initial areas of phallus, and AT means the areas after T days. So as a result, the growth rate of ova from our mascosm experiments were plotted against variations of DIN and salinity by adding different amounts of fresh groundwater. So the growth rates increased by up to 240% for the range of fresh groundwater addition in this experiment, with an average growth rate of 160% for average DIN concentration of harbor seawater observed. So this excess DIN inputs and salinity decreased through submarine fresh groundwater seemed to result in the development of green tides in Jocheon Harbor. And the eastern part of Bangdu Bay, this small semi-enclosed bay, in here also this kind of green tides occurs perennial in the shallow areas. So in this study, I attempted to determine the connection between the nitrogen sources and these ova species green tides occurring in Bangdu Bay. So magnitude, I estimated the magnitude of groundwater discharge using this radium as a tracer, and nitrogen concentration, and also nutrient concentration. So I'll skip briefly. So in this mass balance model, the SGD, the submarine fresh groundwater discharge, accounts the 70% of the total input of DIN in this system, although the water flux, the groundwater water flux is 1 order lower than the saline groundwater, but it acts as a major role on DIN input in this base system. And also, I used this dual isotopic information and sources, nitrogen sources in this bay might be originates soil organic matter mixed with fertilizers, but the contribution of soil organic matter was considered to be insignificant on this volcanic island because it consists of highly permeable basaltic rocks, overlain by thin soils. So the study suggested that the rapid infiltration of nitrogen fertilizer and subsequent leakage into the coastal ocean through SGD results in green tide massive occurrence in the coastal waters of this high permeability volcanic island. And I'll show another research result related to groundwater and Jeju ecosystem. The sampling was conducted at the coastal waters of Seogwipo here, the southern part, and Halim, the western part. In Jeju, there is a distinct difference in biological community structure between the southern and western part of this island. And in Unsam and Seopsam here, located in the southern part, near the stations 6, 7, and 10, brown seaweed covered 50% of the total algal biomass, but this corals is the dominant benthic species in Biangdo, located in the western part of Jeju. So based on this, the distributions of ecological communities in the southern part and western part, the near stations were chosen to look at the effective SGD, and outer stations here were used to observe the background conditions. So the activities of radon-222 in seawater were measured by red 7, and this is the plot of salinity versus radon-222. So the source of lower salinity water in the southern part, the black and blue data, it shows the groundwater source, because this radon-222 activities in groundwater were 2 to 4 orders magnitude higher than those in surface water. This figure shows that fresh groundwater is clear source of nutrients, BIN, in the southern part here. But in contrast to southern part, the lower activities of radon-222 in the low salinity surface water of western part indicate that the source of the fresh water in western part is likely from surface runoff or precipitation, but this fresh water is likely from local stream waters or unlikely from local stream waters or precipitation, since there is no local streams and a little precipitation at the time. So during summer and fall season, the CDW, Changjang diluted water, which is one of the main nutrient sources in the northwestern Pacific marginal seas, flows even into the west of Jeju Island and is introduced into the Jeju Strait. So since the concentrations of nutrient decreased sharply from the Changjang River discharge and depleted within 200 kilometers from the river mouth, the lower concentrations of radon and lower concentrations with BIN in this western part indicate that likely originated from this fresh water source, originate from CDW. And this organic carbon and the fluorescent organic dissolved organic matter data show that overall these shows a negative correlation against salinities in the southern part, where the fresh water is mainly supplied by fresh groundwater. This DOC and FDOM showed significant negative correlations against salinities, indicating that the higher FDOM, higher DOC originates from fresh groundwater. And this result consisted with the result of the previous studies which conducted in this area. And in the western part, the red data set, where the fresh water is supplied mainly by CDW, the atom concentration is surface. The surface is the closed circle. Surface water value showed no significant correlations. Also deep water. Also, both surface and deep water data showed no correlation with salinity. So, although Changjiang River water is the major source of DOC and FDOM in the North Pacific, the marginal seas, but these intensities decreased by approximately 90% within the long transport from the estuary. So this lower FDOM in the surface water of western part is characterized by the CDW. So we can conclude that the lower salinity waters in the southern part were characterized by higher nutrients and the FDOM, while those in the western part showed no trend. And this difference appeared to be due to difference in origins of fresh water and based on a significant negative correlations of salinity and radon-222 activities, the main source of nutrients, and FDOM is found to be from fresh groundwater in the southern part, but fresh water from CDW occurring in this western part traced by lower radon activities displayed lower nutrient and high dissolved organic matter. And this high nutrient concentration in southern part may provide favorable conditions for the growth of the seaweeds, while relatively low nutrients concentration and high FDOM concentrations in the western part provide favorable conditions for survivals of corals. Okay, so almost one hour is left. So recently the Inha University where I worked is located in Incheon, where tidal floods are widely spread. So the next step is I will focus on the SGD study in this Korean Gyeombul tidal flood. So this is one of case study. Recently, researchers have highlighted the role of coastal ecosystems under global warming with respect to coastal protection and buffering and for regulating blue carbon services. So coastal sediment represents a dominant reservoir of sequestered organic carbon in marine environments and has an important ecological role in global biogeochemical carbon cycling. And salt marshes and mangroves and seagrasses are representative blue carbon habitats due to their serving as highly efficient CO2 sinks. But unfortunately, Korea has a particular absence of mangroves and a very small area of salt marshes and seagrass beds. However, we have large area of tidal flats, about 2,500 square kilometers. And this is the result of domestic research team published in Science of the Total Environment in 2021, the last year. This study is the first document estimated organic carbon stocks and sequestration rates in the Korean tidal flats. Using field and remote sensing results, they estimated total organic carbon stocks and sequestration rates in the tidal flats of Korea at first time. So this study presented the first report of blue carbon potential in Korean tidal flats, providing baseline information on the carbon dynamics. But they are, I think, but they are missing a very important fact. They do not consider the exportation of carbon, such as SGD and pore water exchange. So in addition to this, I am now going to look at the flow patterns and fluxes and ecological responses of tidal flats in Korea, including Incheon. So I hope I can show more interesting results next time we meet about the Korean tidal flat and SGD. So thank you for listening. It was an honor to be able to have the final presentation of the year. So if you have questions, please feel free to ask. And okay, I hope everyone stays healthy. Thank you.
Thanks, Hyung-Mi. A lot of very interesting stuff. All right,
Yeah.
everybody, if you have questions, just show your hands or just turn on your microphone and ask. Oh yeah, I have one. So in your first story, for the global reassessment, SGD neutron fluxes assessment, when you use the N members, the saline groundwater N members, you get the new SGD fluxes. So when you use the SGD fluxes to calculate the nutrient fluxes, did you use the same nutrient N member, or you also use the new nutrient N member, which has the the salinity is also higher than 10?
Yeah. Oh. So you mean the which N member for the nutrients, for estimating nutrient SGD derived nutrient
Okay.
fluxes? So
Yeah,
as you
so
can
you
see
use the
figure,
yeah.
the nutrient concentration is also quite constant at salinity values over 10. So I use this salinity over 10 data sets for the nutrient and member values for avoiding overestimation.
Okay. For your second story, it shows there's a inverse, that is a decreasing trend between the pH and what is the x-axis? So it's a decrease. In the lower salinity and you have the higher pH, lower DIC. You said the offset is because of the utilization of primary producers, right?
Sorry.
Yeah. Next one, I think.
Next one, this slide.
Yes, there's a story, but when you explain the story, you said it's because of the yes, this one. So my question is, the plots, the E plot, which is the DIP, why DIP is not to be utilized?
Oh,
DIN and the
actually, it's not my own study. This is my colleague, and this Kim is Cubum. So I
okay.
think they use only DIN variations between this Hwasun Bay and this base system. SGD derived nitrogen flux is very large, but it is very effectively, very rapidly decreased in when it reaches to the basic water. So they estimate this any primary production amount of primary production by using this the variation of nitrogen concentrations, I think.
You mean the DIP is also utilized, but is utilized much faster?
Yeah, maybe. And then the IP, they're a very large source of the diffusion source from the bottom sediment for the DIP in the space system. So they use the DIN only, I think.
Okay, thank you. Any more
Yeah.
questions? Natasha?
Hi, Bochao and Hyung-Mi. Thank you for the interesting talk. It's a lot of data and difficult to digest all of it. So I'm interested in similar question that Bochao just asked about the pH changes. And I just opened the study that you cite, Lee and Kim in 2015, but I haven't had the chance to go into details. So maybe you can explain to me why pH is increasing when you have high primary productivity.
So your question is why pH is
Well, increasing.
Why pH increasing when the primary production increase?
Mm-hmm.
Because simply we can think the primary production consume the dissolved inorganic carbon, the CO2, like.
Mm-hmm.
So the decreasing CO2, decreasing dissolved
Right.
inorganic carbon,
Mhm.
which corresponds to the.
Right. And I'm just thinking, I agree with you exactly that if you have high primary productivity, you have instant increase of pH because of consumption of CO2, DIC in water. But then
Yeah.
this is at the very preliminary stage of the whole story. Then organic matter starts decomposing and you would see decrease in pH. So most likely the overall would be decrease of pH, if I'm right. But Charlie is shaking his head. I'm assuming he agrees.
Yeah, yeah. Sorry, is the double side of the same story.
Right.
Actually, I'm sorry for that. This part, this pH and the IC part is not my part, but I didn't think
That's
that
okay.
you are interested
I'm
in
glad
this
that
part,
actually,
especially.
yeah, I'm glad that you actually brought it up because I think it's a very interesting pH dynamics that we can look a little bit closer. And I don't think there are that many studies that have looked at those correlations. And I have one more question, which is related to nitrogen contaminations. You mentioned twice that you suspect that nitrogen contaminations are the reason for, yes, that slide in Huasan Bay. How do you know that it's not nitrogen that is a legacy of nitrogen stored in the soils instead of freshly applied fertilizers?
Oh my God.
Because I'm just going to give you a little bit background. We suspect in some of our studies that the nitrogen, we looked at, records of applied total nitrogen as fertilizers in the areas, and we see that people use less and less nitrogen, but we continue to see nitrogen in the system. And the question is why, if we decrease the nitrogen, we continue to see nitrogen in groundwater. And so one reason is that perhaps those soils have been overloaded through time with nitrogen, and it continues to leak in the system, in the groundwater system. Do you have any insights of, what is the nitrogen applied as fertilizers in this area, whether they have increased or decreased this application?
Yeah, I'm not sure I clearly understand your question. So you are wondering that my
If this
opinion
is, if this is
about
old nitrogen that stayed in the soils, or it's, so to speak, newer nitrogen applied.
I think is first in this volcanic island, the soil organic matter, organic nitrogen contents is very low, negligible portion, and they also measured the nitrogen isotopic values, so it corresponds to the artificial fertilizer values. So and also the spring season, the agricultural activity is very high. The ion concentration is especially high in this season. So based on that regions, they concluded this nitrogen contamination is affected by the fertilizer, the excessive use of fertilizer.
Yeah, that's interesting. In the spring, they probably apply most of the fertilizers in the spring, because you can see, although spring is also your wet season, right? When you would see more precipitation and therefore more runoff and more sort of dynamic nitrogen transport. But if you know for sure that they are applying it in the spring, then it makes sense that the DIN is higher, much higher in the spring compared to other seasons. Thank you. Very interesting. I appreciate it.
Thank you, Dimova.
Okay, Tami. Your turn.
Yeah. Thank you. What a nice presentation. My question is just based on out of curiosity. In your slide 14, you showed some estimate for evapotranspiration. So I'm wondering how you get the value for the evapotranspiration in that data.
Sorry, I cannot hear you. So please one more. One more time.
Yeah, interested in knowing, August, in your slide 14, you showed some estimate for evapotranspiration value. So I'm wondering how you calculated your value, how you got the estimate for the evapotranspiration in your site.
You mean the global scale study?
Yeah, slide 14, please. Slide number 14.
This
slide number 14.
Yeah.
This slide.
The evaporation percentage here.
Evaporation percent here. Actually, this values is from the other study, the reference value, not measure this value by myself.
Okay.
So there are many studies conducted in this Jeju Island water budgets, not our oceanographers, but many geologists and many other researchers have interested in this island water budget. So there are many values I can found that from the literature surveys. So yeah, the evaporation values were also from the other previous studies.
Do you have any idea on how they got the value?
maybe I have to study about it.
It's fine. It's
I'm
okay.
sorry. I'm sorry.
It's okay. It's fine. Thank you very much.
All right. Homie, I don't think there's any further questions. I'd like to thank you again for a wonderful presentation. Also thank everybody for the update. And I guess I'll see you guys next year in 2023. All right.
Bye.
Bye-bye.
Bye.